In this video, we're going to learn how we can combine convergent sequences to obtain new convergent sequences, and this same theorem that allows us to do that will tell us how we can compute the limit of sequences in a more efficient way. So imagine that I have a sequence an that converges to L and a sequence bn that converges to M. Then I want to build a new sequence whose terms are given by an plus bn. Can I say that the limit of this new sequence is L plus M? That is, can I say that the limit of the sum is the sum of the limits? Well, the answer is yes. And this is great. It's going to make our life so much better. And that will be the main focus of this video. But before we do that, I want us to go back to an exercise that we did before. If we want to find what is the limit as n approaches infinity of 2n squared minus 1 over n squared plus 1? Well, we did it before. We know that the limit is 2, but we had to use the epsilon definition of the limit, and that is hard work. It is difficult and it takes time. So can we find this limit in a more efficient way? So let's see what we would like to do, and then the next theorem is going to tell us that indeed our dreams can come true and that we would like to do is indeed allowed. So you see, if we start with this and I divide the numerator and the denominator by n squared, we end up with the limit as n approaches infinity of 2 minus 1 over n squared over 1 plus 1 over n squared. Now, 1 over n squared is the same as 1 over n times 1 over n. So let's do that. But we showed already that as n approaches infinity, 1 over n goes to 0. So then the question is, can I say that this limit is then 2 minus 0 times 0 over 1 plus 0 times 0, and therefore the limit is 2? The answer is yes. And the following theorem, that's called the limit law for sequences, is going to tell us all the rules that we can follow to justify all the steps that we just did. Okay, so this theorem tells me that if I have two convergent sequences, an and bn, and I know that an converges to L and that bn converges to M, then the limit of an plus bn is equal to L plus M. That is, the limit of the sum is the sum of the limits. Also tells me that if I pick any real number c, and I consider the sequence whose terms are c times an, this sequence converges to c times L. Point number 3 is telling us that the limit of the product is the product of the limits. And the last one is the one that we have to be a bit more careful about. You see, we're never ever allowed to divide by 0. So, how can we make sure that this makes sense? Well, in order for us to be able to define the terms an over bn, we first need to know that the bn's are never 0. So that's why I'm imposing that condition, that all the bn's are not 0. And again, if I would like to say that the limit of the quotient is the quotient of the limits, and I want to write L over M, I need to make sure that M is not 0. But if we're careful and we know that the bn's are not 0 and that M is not 0, then indeed we have that the limit of the quotient is the quotient of the limit. Now, we're going to show point number 1. I'm going to prove to you that the limit of the sum is the sum of the limits, and I will leave for you as an exercise to prove the other 3. Great. So how can we prove this? Well, the first thing that we should do whenever we want to prove something is write down what we want to show. We need to make sure that we know what we're trying to do. So here we don't have much to go with. We have to use the definition. And the definition is that, well, for every epsilon positive, there exists an n, a capital N, such that if n is bigger than capital N, then the absolute value of an plus bn minus L plus M is less than epsilon. Okay. And then, well, we have here a statement that has a bunch of quantifiers. We've seen statements that look like this before. So what I want you to do is please pause the video and try to write down the structure of this proof. You don't need to worry about writing down all the details. The only thing that I want you to do is write down all the steps that we need to follow to prove this statement. When you're ready, please come back. Welcome back. So let's see if your proof structure looks similar to my proof structure. Okay, so this is what I think we should do. We should first fix an arbitrary epsilon, which is a positive number. Then we need to take n equals something, right? Because remember, we want to show for every epsilon there exists an n. So we need to take n equals something, and then I need to show that my n works. And in this case, I want to show that if n is bigger than capital N, then the distance between an plus bn and L plus m is less than epsilon. So we need to assume that n is bigger than this capital N that I found, and then I have to conclude that indeed I have the desired inequality. If your proof structure was not correct and it looks very different from mine, I invite you to watch a previous video when I go into more detail about why this should be the proof structure. Okay, now that we're clear on what the structure should be, let's try to find n. Remember, I've told you before, the difficult bit in this proof is always finding n. So how can we do this? Well, we're going to start by fixing a positive epsilon. Good, out of the way. And now, let's see, we need to find a number n such that if my n is bigger than this number capital N, then the absolute value of an plus bn minus L plus m is less than epsilon. Okay, so we don't have a lot to work with here, but I feel that we should start with the right-hand side of the inequality and see if we can find the conditions for that to happen. So, okay, the first thing that we can do is, well, we know that we have that an converges to L and bn converges to m, so it would make sense to put the an's and the L together and the bn and the m together. So we just massage this expression using commutativity and associativity, all those things that you already know, to rewrite it in a more convenient way. And now I would like this quantity to be less than epsilon. That's what I want to happen. But the only things that I have at my disposal is that I know that because an converges to L, I can make the distance between an and L as small as I like. And because bn converges to m, I can make the distance between bn and m as small as I like. So what I would like you to do is pause the video and try to think of a way of connecting this quantity that we have here and the absolute value of an minus L and the absolute value of bn minus m. And when you're ready, please come back. Great. So if you said that you wanted to use triangle inequality, well done. That's exactly what we wanted to do. Here you see, we're going to break this big quantity into two ones that are, simpler to work with. We have more information about. So what we're going to do is we're bounding this quantity that we would like to be small by the sum of two quantities that we know we can make small. Okay, so now if I wanted this whole thing to be less than epsilon, that would mean that the sum of these two bits will be less than epsilon. I have two bits and I want the sum to be less than epsilon. A natural way to do that is, well, make each one of them less than epsilon over 2. If I manage to do that, I'll be done. It'll be perfect. So how can we do that? Well, remember that we know that an converges to L. So for any positive number that I pick, let's say epsilon prime, I can make the distance between an and L less than that epsilon prime. Remember, it's any positive number in the world. So if I take that epsilon prime to be epsilon over 2, then I can find an n such that if little n is bigger than that big N, then the distance between an and L is less than epsilon over 2. And now we can do the same thing with the bn's, right? We know that bn converges to m, so then I can find a capital N such that if n is bigger than that capital N, then the distance between bn and m is less than epsilon over 2. Now, here we have to be very, very careful because these n's could be different. And that could be a bit of a problem. And to be honest, most likely they are going to be different. So to go around this, what I'm going to do is I'm going to add labels to these n's to make sure that I don't get confused. So you see the n that comes from the sequence an, I'm going to call it n sub a. And the n that comes from the sequence bn, I'm going to call it n sub b. But now look at this. I need both, that the distance between an and l is less than epsilon over 2, and I also need that the distance between bn and m is less than epsilon over 2. Now, to guarantee that, I would need that n is bigger than capital N sub a, and that n is also bigger than capital N sub b. So we need n to be bigger than both, na and nb. Well, there are many ways of choosing one that is bigger than both, but a natural way to do that is, well, if I take n to be the maximum between na and nb, if I know that n is bigger than this capital N that I just defined, then n would have to be bigger than both na and nb. So now that we have our n, we're happy, this is great. We just need to worry about writing down the formal proof, putting all the bits together to write down something nice and polished. Remember, this was just how we came up with the idea of the proof. Now we need to write it down. Okay, so let's start. As always, we will begin with fixing an arbitrary epsilon positive. And then, well, we need to use these facts. We need to use the fact that we know that an converges to L, and we need to use the fact that Bn converges to M. And here we're going to apply the definition of limit with epsilon prime equals epsilon over 2. Remember, that's what we did. And if we do that, then we know that there exists an NA such that if n is bigger than NA, then the distance between AN and L is less than epsilon over 2. And there is an NB such that if n is bigger than NB, the distance between Bn and M is less than epsilon over 2. Very good. And now that we know what NA and NB are, I can define my capital N to be the maximum between NA and NB. And now all I have to do is to show that indeed that choice of capital N works. How do we do that? Well, we're going to assume that N is bigger than capital N. That means that N is bigger than both NA and NB. Now, by 1, we know then that the distance between AN and L is less than epsilon over 2. And by equation 2, or statement 2, we know that the distance between B and M is less than epsilon over 2. And now we want to use this to our advantage. So how can we do that? Well, remember where we started when we were doing our rough work? Now we're going to just redo it. We know that the distance between AN plus BN and L plus M can be bounded above by the sum of the distance the sum of the distance between AN and L and the distance between BN and M by using the triangle inequality. But we just said that these two distances are each less than epsilon over 2. Well, we end up then that this is less than epsilon over 2 plus epsilon over 2, which is epsilon. And that's exactly what we wanted. So indeed, we have shown that no matter which positive number epsilon we pick, we can always find an n such that if n is bigger than this capital N, then we obtain the fact that the distance between AN plus BN and L plus M is less than epsilon. Okay, this proof is hard and it has many important things that we have to be very careful about. So what I wanted to do is I wanted to look at the tricks of the trade. There are many secret tricks that appear in this proof that we're going to use over and over and over again. Okay, the first one, the triangle inequality trick. We bound a quantity that we want to show is small by the sum of two quantities, each of which we know are already small. trick number 1. We already used it, remember? Trick number 2, what we call the epsilon over 2 trick. Apply the definition of limit with epsilon prime equals epsilon over 2 to end up with an overall bound of epsilon. We did it again, right? We had 2 bits, we made each bit less than epsilon over 2, so the sum was less than epsilon. And then the last trick. Take n equals the maximum of the n's that you had, in this case maximum of na and nb. So if you choose n to be larger than all of the values of n that are involved in my proof, that will ensure that if n is bigger than this capital N, then n is bigger than na and nb. These 3 tricks that we saw here, we're going to see them over and over and over again in analysis. And that's why I wanted to share them with you. I want to share all the secret tricks of the trade that we use all the time. You will see throughout the rest of the term, these tricks will appear. Sometimes the epsilon over 2 trick is going to be maybe an epsilon over 3 trick, because we're going to bound the quantity that we want to show is small. We need to bound it by maybe 3 bits, and each one of them would have to be less than epsilon over 3, so the total adds up to epsilon. Maybe we'll take the maximum of not 2 n's, but maybe 3 n's, but the ideas are always going to be the same. And to finish this video, to wrap it up, there is something I want to discuss with you, because I know that many students struggle with this. And it's the difference between proving convergence and using convergence. And this is what I mean. If I want to prove that the sequence xn converges to L, we are given an arbitrary epsilon positive. I do not get to choose it. And I must find a value of n that works for this epsilon. Now, when I want to use the fact that yn converges to m, let's say, first of all, I can choose any epsilon I want. I get to pick it. And I know that it's guaranteed that there is an n that works for my choice of epsilon. So, to summarize, these 2 things are very, very different. When I want to prove that a sequence xn converges to L, I cannot choose epsilon, and I have to show how I produce the n. Versus when I'm using the fact that the sequence converges, I can choose the epsilon, any epsilon that I want in the world, no matter how crazy it is, as long as it's positive, of course, and the n will be given to me. It will be given to me by just the fact that I know that the sequence converges. So in this proof, for example, we wanted to show that a sequence was convergent, using the fact that other 2 sequences were convergent. And this is how these 2 ideas play together. And you will see, we're going to use these ideas over and over again, so make sure that you understand them very well.